right, let's get started.
Right.
The Stanford Center for Carbon Storage is pleased to present this workshop today on Bridge Energy's CCS project in the Brea Olinda oil field down in Orange County. So the first speaker and the main speaker today is Randall Breitenbach. He's the founder, CEO, and chairman of Bridge Energy. He also co-founded the Pacific Coast Energy Company, BreitBurn Energy Company, and BreitBurn Energy Partners. He served as co-chief executive and chairman of the board from 1988 until his retirement in 2012. He's clearly not retired. Randy also served as the chairman of Stanford University's Petroleum Investment Committee in 2007 and is currently a member of the Alternative Energy Investment Committee. He's also a member of the Carbon Capture Usage and Storage Roadmap team called CCUS, reporting to the Department of Energy. He also serves as a trustee and is chairman of the board for Hotchkis and Wiley Funds, a large mutual funds company. He holds a B.S and M.S degree from Stanford, from the department formerly known as Petroleum Engineering, now ERE. And he also has an M.B.A. from the Harvard Business School. So today's discussion is going to be what we call workshop format. What we'd like to do is Randy and his team will be presenting. There will be some very obvious breaks where they will pose questions or pauses to the group for discussion. We would like everyone to keep their microphones muted, but if during the presentation, even in the middle when we're not at one of those pause points, if you have a question that you think is important to get out for clarification, please unmute yourself, ask the question, and then remute yourself. But there will be times when we try to get everyone to unmute to get some discussion flowing, and then we'll go back into the presentation format. You can also use the chat function if you would like. We will, at the end of it, save the chat so that if there's any message or anything that you want to send to Randy and his team, you can do it at that time. And as Randy will be the main presenter, but we'll introduce some other folks from his team to also present portions of the project. So without any further ado, if everyone would please mute their microphones, and I will hand it over to Randy.
Thank you, Sarah, and of course, good afternoon, everyone, and thank you all for joining today. We are very excited, honestly, to be on this call to talk about our project. It's been over 2 years that we've been working on this. A large portion of that time has been building the 3D geologic model that we'll be looking at later in the presentation today. And it's been very fulfilling, honestly, to see it all start to take form. We've also developed a short presentation on our CO2 project here in Brea, as Sarah mentioned. If we're able to get the Zoom technology to work, like I said, we'll go through the 3D geologic model as it is in its current form and try to answer any detailed questions that may be asked. We'd like to, as Sarah said, keep this as somewhat of a working format. So I will stop and ask questions if there are any questions at certain points. But also feel free to interject, and I don't know how you do that in Zoom, but I think you can probably like raise your hand sort of thing, and we can stop and answer the questions. We really are not under any time constraints here. But before we get into the presentation, I'll tell you a little bit more about us and where we came from. First and foremost, excuse me, I'm obviously a very proud alumni of Stanford. I've tried to stay involved with Stanford through the years and worked for the School of Earth Sciences Pick Endowment for almost 3 decades. Honestly, this has allowed me a good reason to come back to Stanford and see the beautiful campus and catch up with old friends. It was on one of those visits that I met with Sally and Tony, and we discussed some of the small projects my company at the time has been working on to reduce our environmental impacts. And in particular, this concept of zero emissions facility was discussed, and also ways to be smart and actually use our current emissions in an economic way, which is an interesting way of turning this upside down. We also talked about renewables and how the costs had come down dramatically. I was actually very blown away by the contracts that Stanford was able to get via renewable energy, and it set me off on a different direction. But it was because of these discussions that I ultimately got involved with running some senior projects at Stanford on one of the facilities in 2018. The senior projects that I worked with Tony and Sally were very, very interesting and fun concepts. The first idea was to use a genetically modified algae to convert the CO2 into plant lipids that could be extracted and blended in our oil production. It was very out of the box. That idea unfortunately hit some cost and sizing issues and was not deemed economic. But the second idea was to blend the flue gas from our power plant in a big mixing tower with our produced water. And that would allow the CO2 to dissolve in the water and basically carbonating the water before we inject it back in the ground. We ended up testing that idea in a lab in Scotland, and it actually worked. So we've really moved forward in that concept, and you'll see that it kind of permeates throughout the rest of the discussion. There are some issues, but it's definitely still a part of our potential plans. As Sarah mentioned, I'm also on the carbon capture team. I was on the roadmap to deploy for the storage subgroup. And obviously with Sarah, who just obviously introduced me, she's the managing director for Stanford Center for Carbon Storage. So we got the right people on this call, that's for sure. And of course, I need to say something about Professor Tony Kofasek, who I worked with on most of the senior project, and his help on the carbonated water concept was invaluable. So again, I'm kind of overall, I really would like to make this a working meeting where we try to identify some of the most troubling hurdles to a completed and successful project. We certainly want to avoid any of those future oops moments where I wish I had not forgot about that issue. So I want to make sure everyone feels comfortable with the direction that we're going and tries to help us point out any like glaring issues that you see. And to that end, maybe there's a way to set conservative guidelines or technical parameters or injection specifications or something that we can help define whether a storage location will pass, because we're going to want to, this isn't going to be the only project for this to really work. There are going to have to be multiple projects that are similar to this rolled out across the state of California for it to work. So with all of that, why don't we get into the presentation? Also presenting with me is Ben Davidson. He works here with me at Bridge as a geologist. He has his master's in geology and has been instrumental in helping build the 3D geologic model with the strong support from John Harris, who is will also be speaking. John is the co-founder and president of Numeric Solutions, and one of their areas of specialization is risk analysis of underground storage facilities. Also joining on the call is Richard Schultz, Dr. Richard Schultz. He received his PhD in geology from Purdue and specializes in geomechanics of faulted, overburden, and reservoir systems and in natural gas underground storage. So I think we have a nice cross-section of experts here to really take a look and evaluate this project in a meaningful way. With that, Ben, if you could help bring up the presentation and we'll get started. Make sure here. Just a second. Make sure I get this right. So, Ben, why don't you turn to page 2 real quick? Let's see here. Okay. All right, well, here's the second page. So this obviously is just a short overview on Bridge Energy. Bridge was founded, and as you can see, in 2017, and is a partnership between myself and KKR's Energy Income and Growth Fund. If you were to look at our website, it's a fairly short website. We were formed to evaluate all forms of energy and energy storage necessary to fuel the California economy safely, cost effectively, and with minimal environmental impacts. Our tagline is bridging to the next energy paradigm. The reality is we're going through a massive energy transition And it, like I just said, it's massive in size and scope. And California's demand for energy is insatiable, and it's currently running on the order of 3 trillion watts. So this idea of a transition from fossil fuels and where we are to a fully renewable system is going to be extremely complicated and expensive. And we are looking as a company or as a partnership at ways of providing or looking at those opportunities and trying to participate in those opportunities. The first acquisition or first investment that we did as a partnership was acquiring the Brea Olinda oil field. And we did that in July of 2017. It's the second largest, the Olinda landfill is the second largest landfill in the state. That was not by coincidence. Interestingly, as I said, Brea oil field is massive in size. In fact, the LA Basin is the second most prolific oil basin in the world per aerial acre. People don't realize that at the turn of the last century, there was such a significant amount of oil being produced from the LA Basin that it overwhelmed the economics of many countries. The Brea Olinda oil field itself was actually the very first oil field discovered in the state in 1880s. And if you were to see that movie, I think it was called There Will Be Blood, it was loosely based on Ed Doheny. And interestingly enough, he discovered that, like I said, he discovered that field in the 1880s. And it was, like I said, it's massive. It's 2.3 billion barrels. It was, they produced approximately between 400 and 450 million barrels to date. That's a very small amount of the original oil in place. And its peak production didn't really peak until the 1950s, which is unusual. Most oil fields produce the most when they're the highest pressure. This is so complex and spread over such a large area that it took a while to get to peak production. Probably the more important issue as it relates to this and why we're talking today is the fact that water injection or disposal in the Brea field really didn't start happening until the 1970s. And what that means is that it's just been drained. And even at post 1970s, all that was replaced was being used as a disposal of the produced water that went with the growth stream. So you're never actually even putting back in the ground at any point in time in its history. Are you putting more fluid back into the ground to catch up, or what we would call fill up? So the field is incredibly depleted, which means that it's very good and a very strong candidate to take on additional liquids. So kind of overall, we like to look at this. It's almost kind of like, like an old real estate project, if you will. We like to look at this old oil field as not only an oil and gas field, but to potentially repurpose it and turn it into what could also be, as you're producing the oil, included as a waste gas disposal site. We're sitting right next to a landfill, and why not put a gas disposal site right next to it? It makes kind of, obviously from our perspective, it makes total sense. So why don't we jump to the next page? Thank you. Here's just some quick facts on the Brea oil field itself, albeit they don't really impact the CO2 sequestration and EOR project. There are approximately 300 wells. We have 22 injectors. The gross production is currently about 2,500 barrels of oil per day. The one thing that we do have is a very high oil cut. Again, because of the lack of water injection, our oil cuts, in some wells are as high as 20 and 30%. The other thing that is a real benefit is we have a very low decline rate. It allows us to have a cash flow stream that's relatively flat into the future. We produce from the Miocene and the Pliocene zones. Their general depth is between 3 and 5,000 or 3 and 6,000 feet. And as it compares to other properties or other oil fields in the area, we have dramatic dips. As I said, it's because of those dips we have we are benefit from gravity drainage. The rock in the area tends to be harder, and our oil tends to have a higher gravity, and as I said before, very low pressure. Jump to the next page. Here's a more detailed map of the area. You can see there, you know, where it says Olinda Landfill, that's the area of the landfill. And if you can see that little yellow area under the Brea office location, that's where our office is. And so you can't get much closer. And the reason I show this map in detail is to give you some idea, though, of the complexity of the land ownership in the area, which does come into play. Obviously, the close location of the landfill to our facility, but also the urban encroachment around the edges. And that happens in just about every field that you'll find in the LA Basin, for sure in the LA Basin, but it really throughout California now, it's happening everywhere. These oil fields have been there forever, way before the urban environment, but it's encroaching, and it has been encroaching for decades. And it does, you know, causes concern, as you would expect. Turn to the next page. Thank you. This is actually an aerial view of our office location. It's really large in size. So if you can see the blue section that's not a rectangle, that's approximately 2 acres. And the other area to your left is approximately 1 acre. The point of this is we've got plenty of land up there to accommodate different facilities, depending on how we want to build this out, and if we feel we need to drill additional wells to get to different locations to inject, we can also use some of these areas. But that said, you know, as you saw on the previous page, the field is extensive and runs and covers several thousand acres. Let's go to the next page. Here's a kind of generic landfill. It's titled, and just a second, my phone. Turn off my phone. Sorry. So this is a generic landfill, and so really what happens here, and I'll just go through the simplistic description. You basically build multi-acre blocks of trash that are encapsulated in impermeable dirt and clay. You pre-pipe those blocks. That allows the gas and fluids to escape during decomposition. Each of those blocks takes about 5 to 7 years before it really reaches its max flow rate, if you will. And then it dwindles from there. But as you continue to put in trash, it continues to produce gas. And the life of this field is expected to be for another 20 to 30 years, given the size. And we would expect then the life of the field in terms of gas emissions to be an additional 7 to 20 years past that. But that's that's the real basics. Currently, what they do is they take all of the gas off of this field and they run it through some large turbines. They have on the order of just over 30 megawatts. They're currently running about 25 megawatts of that facility. They generate a lot of electricity, and they basically sell it into the city of Anaheim at a preferred price. That said, that allows them to burn the methane, which obviously has a lot higher global warming effect. So they do get rid of the methane. However, the CO2 and everything else comes off of that flue gas and goes directly into the air right now. So because it's considered renewable gas, they don't have to be a part of the cap and trade program. So they're not paying, and it's a state agency or county agency. They don't pay or have to participate in the cap and trade regulation. So, and like I said, which, it costs somewhere on the order of, currently it's trading at about $17 a ton. So, if they're like I said, they're emitting about 270,000 tons in flue gas. So it's a significant amount of CO2 and a very large concentrated source, considerable for the state of California. So we'll go to the next slide, please. Here's where I try to talk a little bit about where are the different possible sources. And interestingly, each of them has its own issues. Now, they're all different, but there are different take points where you can take it off the landfill. So let me kind of walk through the description here and turn this thing off. Someone keeps trying to call me. Silent mode. As you can see, the first thing is the gas comes directly off the landfill. It's on a very small vacuum. You can see 45 inches. It's pulled with these big extraction blowers, and the gas comes out. It's raw gas. It's pretty nasty stuff, but it's about 40% CO2, and it's running at about 95 to 100 degrees Fahrenheit. The gas blowers then push it up to push it forward into the system. They get it up to, it's about 4 pounds. So the take point there, if we decided that was where we want to take the gas, that's the characteristics. And then the next step that it goes through is the gas is then run through some chillers and to drop the water content out. And then it's increased and compressed by compression to 105 pounds. That compression obviously increases the temperature, and the temperature increases to about 115 to 130 degrees. It then is cleaned up a little bit, and it's supposedly at that point free of water and what they call siloxanes. And that's some nasty stuff. And so, you know, the question then is, is it better to take it, or more cost effective to separate the CO2 at 105 pounds and 115 degrees? And then the next step is they take it to 250 pounds approximately, which then again further increases the temperature due to compression, and you're up to between 140 to 145 pounds. And then they run it through the turbines. All of those sources, all of those take points, you know, if I were to remove 100% of the CO2, I would get 160,000 tons per year, approximately. And that would be 100% efficient. Then they run all this through their turbines. And the turbines, you know, obviously they generate gas, generate electricity, and they burn the methane. And the result is that you pick up quite a bit of more CO2 because you're burning the methane. So now you go from a source of 160,000 tons to 270,000 tons. So you could pick up an additional 100,000 tons. The problem is that the temperature is super hot. It's actually even cooled down. It comes out of the stack, but that's after cooling. Normally right off a turbine, it's about 700 to 800 degrees. Not easy to handle. So they cool it with some water through some water towers, and they drop it to 320, but it's still 325 to 350 degrees under current conditions. But you now have 270,000 tons. But the other weird thing is that as a part of combustion, they bring in a lot of additional, what they call combustion gas. And that dilutes the CO2 stream down to a 5 to 6%. So you've taken a stream that was 40+% before, and you've now dropped it, even though you picked up way more CO2, your stream's only 5 or 6%. So it becomes a cost issue, right? So, you know, being able to handle this large volume and heat is more of an issue. And so there's, you know, what we're thinking right at this moment, based on our review of different methods of separating CO2, whether that includes amine towers, and we've looked at membranes, we've looked at just about everything. The least expensive and the one I'm most comfortable with is still the antiquated amine tower technology. And I've run several of them, so I feel, and I built one. It was my first company. I actually built one by hand. I built a gas processing facility. So I'm way more comfortable in operating, and they've lasted the test of time, if you will, in terms of their capabilities. So, and from that perspective, the amine tower works best at about 250 pounds. This is like almost optimal, and about 100 degrees Fahrenheit for the gas. So the best location, it looks like, from a cost-effective way, is likely on that third take point prior to burning. And that's kind of what we're thinking right now, but then we lose 100,000 of the tons that will, and we may have to go back for them later, but you understand the conundrum here. So that's, I mean, that's probably more information than we needed, but it kind of tells you the pricing that the project that we're currently pricing is to take the 160,000 tons because it's going to be the most cost effective. And obviously that's going to be the driver for me being able to get the money to get this done. So jump to the next page. With this, I'm going to hand off the geology. I think Ben is going to step in now and talk through this, and I will, actually, before we jump here, this might be a good place actually to ask some questions. Yeah. So why don't I open up the mic, if you will, and if there are any questions, I'm open for discussion.
Do you want to moderate, Sarah, or do you want us to just jump in?
Just jump in, but why don't you go for it, Lynn?
Okay, well, never known to keep my mouth shut when I probably should, but so what's the are the wells in good shape, Randy? Are you think they're okay as you build the pressure by injecting things?
Well, here's what we're thinking, and it'll become more obvious when we go through where we're going to inject. These wells are very old. Yeah. And I mean, a majority are anyway. So the thinking is that we'll target the deepest, most zone because that's the fewest penetrations. And we will likely be forced to drill new wells. And I'm thinking that we drill those new wells as far down structure as we can reach and past all of our producing wells, and maybe even be below the water, what we would consider the oil water cutoff or transition. And my thinking at this point is in some areas where I'm a little too close to urban and I have wells that are too close to urban of running just a carbonated water mix that I don't have to worry about coming out of solution. And it still has a lot, I can run it up to about, I think 1% mole percent at that pressure and temperature, which is about 4 times a Coke can mixture. And I can put, and we've seen in the labs that the EOR results are still very positive, but more importantly, I can get a lot of volume down there in some of these areas, again, that are a little more sketchy that I worry about. In the other areas where I think I can possibly slug more pure CO2 and water, again, it's still going to be in that deepest, most, and below, and again, vertically down dip, if you will, below where all the older wells penetrate. And then the thinking is, in terms of future operation, is that as we see this percolate up, as it will, over time, the wells that are currently producing that are furthest down in the structure that still penetrate the lowest Miocene C, which is what is our lowest producing zone, we'll see that hit those wells and they'll be abandoned as they move, we'll be able to see the front, we'll get real physical data, not just the modeling data. And we will, at those times, abandon those wells as need be, or at least the zone through as it penetrates the Miocene zone, we'll just back up, set, cement plugs and separate or isolate from that point. So it should be, the way I visualize it anyway, is it should be okay, I think.
Yeah, you just, given how close you are to folks who live there, and remembering Aliso Canyon, you just want to make sure you don't have gas getting loose somewhere.
No, that's funny enough, and we'll talk about it a little bit later. Richard and John both worked on the Aliso Canyon project, so the after effect, proving or trying to solve the problem, basically. Yeah. yes, I mean, that obviously weighs heavily on our mind.
We also have a question from Sally Benson.
Hi,
Hi,
Sal.
Randy. How are you?
I'm good, thank you.
So have you thought of seeing if anyone else has a source of CO2 that they would be interested in using for this project? And are there must be pipelines going out of the field, which would then offer right of ways for CO2 pipelines to come into the field.
Yeah, I mean, my thinking is, Sally, is I'm taking little bites, and this is, you know, this is a big bite actually, and if I can get this project moving, and I can get approval to start doing this, the layering on of putting more in the ground once the operations and facilities are already built is a lot easier. And it's also a lot easier for me to understand what the impacts are, both positive and negative. So, you know, I'm kind of flying blind a little bit. The cheapest, closest CO2 by far is this landfill. Mm-hmm. So anything past that is just going to be more expensive. So there is, interestingly enough, another very large landfill called the Whittier Landfill, which is a couple miles the other direction. And it's probably the only other landfill in the area that's still operational. So weirdly enough, yes, that would be my next step. I would go right over there, and there's a field between us and them. It's called the Sandstone field. And, you know, they're currently drilling wells on their field. But yes, I mean, we would expand that look. And honestly, you know, as I said earlier, I pitched this to KKR. So, and their partners, and, you know, it's, you know, their response to me is, show me it works. You know, get through the hurdles, you know, mm-hmm. Show me that you can get permitting, show me that you can get the government to back, you know, and actually make good on their, you know, on their reward system. So
do you have to do a lot of compression to get the CO2 in?
Possibly, you know, again, there's a lot of ifs still there. You know, what we're looking at, again, we'll be coming off, you know, the amine tower at about 250 pounds. Whether we combine it with produced water when we put it in the ground or not, they're going to be different pressure issues. So we still honestly haven't navigated that last step. You know exactly what it's going to take, but no, it's another cost issue. As like everything here, it's a cost issue.
Randall, has there been any stakeholder engagement with the community just to the south of the oil field? And are you anticipating that they might be more receptive to this than other potential communities, because they're used to having an oil field and a landfill in their backyard, and this is going to deal with some of the emissions that are right in their air?
Well, I mean, the way I look at it is currently all 270,000 tons are going right into the air right next to them. So it can't be worse. I mean, I kind of go, okay, even if a little leaked out, can't be worse than 270,000 tons a day, or excuse me, a year. So, which is 700 something tons a day. So I'm like, I know I've been in this business long enough, Sarah, to know that yes, someone's going to have a problem for sure. And, you know, weirdly enough, and my final slide kind of talks about this from a regulatory perspective. You know, it's really interesting that there's multiple ways that you can look at this, and the way that you look at it changes the way that it's handled. And let me explain that a little better. If I were only to carbonate water and inject that, I don't even need a permit. I can do that today. I'm disposing of water. I have a water permit. I'm just putting CO2 back in my water. That doesn't mean anything. It came out of the ground. I'm putting it right back in the ground. I've already confirmed that with the DOG or CalGEM now. I don't even need a permit. I can just do it. If I convert that to slugs of CO2 and slugs of water, then I got a EOR project, which sounds weird. You know, it's really no different once it hits the reservoir, but for permitting purposes, it becomes an EOR project. And that's a whole different set of guidelines. And then even weirder than that is the next step, which is if I call it sequestration and it's not for EOR, then the whole laws change. Now I need to deal with the surface owner because I don't even own the box anymore potentially. So, you know, because I'm the mineral owner and I'm maximizing the value of the minerals, if I would understand as a surface owner that if you're just injecting CO2, that's not what my deal was with you. My deal was you're producing the minerals and then you're out of there. And now you're injecting CO2 and you're gonna leave it there? I don't want it. You know, or why shouldn't I be compensated for that? So there's that, and that's gonna stop a lot of transactions right now because the surface in a lot of these areas has been separated from mineral rights. So there's that big issue. And that's pretty much common everywhere. Where the rights are, you know, the rights have been severed. So you know, that is why, you know, right now I'm looking at this as an EOR project, period. And I'm not even going to call it sequestration because if I do that, then I got a completely different legal game.
And you're into class 6 and everything. Any other questions? Okay, let's continue on.
All right.
So as I mentioned, before you start, Ben, let me just say a couple quick things because that goes back to what I was just saying and was around, you know, we've been focusing on the lowest area, the Miocene Sea. As I said, it's the deepest reservoir and has had significant production. It still has pressures that are in the 1,000-pound range, which is a nice range because it's a high enough pressure to where the CO2 is compressed almost to a liquid type form. It's you know, super critical, I guess. And there are also much fewer wells that penetrate. And as you'll see in the models, as we get into more granular detail, there's a lot of pinch outs throughout the different zones. And we want to start on the deepest, most zone, fill it up and move up structure. You know, and so, you know, the first, you know, what we're just showing you in terms of volumetrics is really just the Miocene Sea, nothing else. But there's there is a lot of different potential down there. So that's kind of the potential. But so I'm sorry, Ben, that's hand off to Ben.
All right. So yeah, 3D geologic model has many uses beyond just this CO2 EOR sequestration project that we have going on. It can be used for planning our next drilling project, creating and viewing well paths, volumetrics calculations like we'll show you, regulatory compliance, including making maps and cross sections. We've done a lot of that. And it also serves as a compilation of data from past operators and even new data that we acquire today. And as time goes on, all that data will just continue to be piled into this one project where it can be quickly reviewed and you don't have to go through countless dusty boxes and folders in your file room to look for that one piece of data. It's all right here, available right now. And so what you're looking at right now on the screen are some 3D cartoon block diagrams, and they just give you a better sense of the structural geology of this area. The colors represent the different zones or formations, and it is important to note here that what's not shown are the lithologic or the vertical and lateral changes in lithology. That's ultimately going to be the key to success of this project, and we'll get a glimpse of that here in a couple slides. And just for a bit of background, in the Brea Olinda field, the Whittier fault zone consists of several steeply dipping thrust faults that run the length of the field. You can kind of see some of them on these diagrams here, these kind of surfaces poking out of the blocks and extending down very steeply. And they have offset in the order of hundreds to thousands of feet. The main Whittier and Tonner faults were active during time of deposition and acted as the basin boundary as these Pliocene and Miocene submarine fans filled the basin, the LA basin. And so consequently, the sands tend to pinch out both laterally and up dip as they approach the faults. In the Miocene zones, deeper down, these red, golden, kind of teal colors, the sands are a little bit more laterally continuous, whereas in some of the shallower zones, like these Pliocene zones, these thinner zones here, are a little more discontinuous laterally. And nearly all the production in this field is from these Pliocene and Miocene zones. On the northern hanging wall block of the Whittier Fault, the extremely deep La Vida member of the Puente Formation, which is considered a source rock for the major, for the LA basin, really was thrusted up along that Whittier Fault and is now exposed at the surface. However, we generally don't consider these rocks as a possible storage site for CO2. So we've kind of left them out of this, this model here, and that saves us time and resources. But we haven't really quite discounted them yet. It's just purely to make things simple on the modeling. So go to the next slide. And before we dive into the more advanced property modeling, it would be good to provide some general background of the modeling process. Typically, all models begin with just dumping in all the data that you have, digital well logs, the formation fault tops, and any other interpretive and cultural data that you might have existing. A structural framework model is built using that, the fault data that you have, and it's used to delineate the different fault blocks that you have in the subsurface. Once that's developed, you proceed with building a pillar gridding network. And this is often a difficult task because you need to get the pillars just right in order for everything to mesh properly. Finally, after defining the surfaces and zones that you have in your field, you'll go ahead and apply a corner, you'll go through the corner point gridding process, which will apply cells throughout each of those fault blocks. And from there, you can go ahead and do property modeling, and you'll be able to get a better idea of what's going on in the reservoirs. On the screen now, we have a couple property models that we've developed. We have a V-shale property model using SP logs, and then a connected volumes model using a simple sand shale facies model. For the V-shale model, the spontaneous potential log is by far the most prevalent well log that we have in the field. Many of these wells are old, and the only logs available at the time that they were drilled were SP and resistivity logs. And the SP log measures differences in electric potential within the rock and is generally a good indicator of either permeable rocks such as sandstones like we have here, or impermeable rock like shales, mudstones. And after some baseline corrections, baseline shifting and corrections, you can convert that log into what represents basically the amount of shale that you have in those formations. And then you can distribute it throughout the model, as you can see here. And with some clever color scheming, you can already start to see some of the sand and shale layers through these formations. On the right is a connected volume model. And what we did here is we created a simple sand shale facies model. And you can use this connected volume method to basically tell Petrel, which is the modeling program that we've been using, you can tell it to look at all these cells that have a similar designated facies, and in this case it's either sand or shale, and it will try and lump them into separate volumes that are all alike. So you can see we have a lot of these different colors which just basically represent a singular connected volume of sand. And in doing so, you can also remove the shales to give you a better understanding of isolated compartments within your field. These property models allow for a first pass at identifying potential reservoirs to store the CO2. We have selected the connected volume in the Miocene C, which is shown by this blue connected volume on the right. And let's see if this works. Arrow options. I had some little videos. Oh, there we go. It's little nifty videos to visualize it a little better. But the isolated connected volume on the right and on the left is just a slice of that V shale model that I showed you earlier. We'll let this one finish. And you can see on this slice of the V shale model that we can get a better idea of the pinch outs up dip and the separation between these different sand packages throughout the reservoir. And I guess it's important to note that, you know, we've identified this Miocene C, which is marked here by the light blue coloring, which is the Miocene C surface. We've identified that as our primary target, but you can already start to pick out some other isolated bodies within just this one slice. And so there will be other connected bodies throughout the reservoir at the Brea Olinda field. And finally, at the end of this presentation, we'll likely end up turning off the presentation, and I can open up my Petrel model. We can spin it around and we can ask some questions and just play around with it. And so now I'm going to pass it on to John Harris and possibly Bruce, and they'll go over the volumetrics. Oh.
Do we want to just take a quick break and see if there are any questions?
Yeah.
Oh, yeah. Definitely. Sorry.
If you have a question, please raise your hand. I will ask one while we are waiting for hands to raise. I believe there's been some recent seismicity on that Whittier fault. Eventually, once you inject CO2 into this Miocene C, how close will the CO2 plume get to the fault?
That's a good question. I think we're going to be discussing some containment and monitoring scenarios that could possibly be implemented. I think we're looking at anywhere on the order of hundreds of feet, depending on where we place this injector for the CO2. And one good thing about this field is because it has so many wells, there's going to be a high density of wells that are going to be up dip in that same formation. We'll be able to map that plume and be able to analyze it better, but I don't think we have any sort of idea yet as to a more accurate measurement on how close it could possibly get.
Yeah, I mean, Sarah, I mean, we are still kind of pondering what is the best methodology, and like all of this stuff, it gets driven by permitting. You know, if I could do it how I wanted to do it, I would be injecting CO2 and slugs of produced water as far down structure as I possibly can. Watch it percolate up via both my model. You know, I'll have a 3D simulation running and see what that front looks like compared to actual real monitoring from the wells that are producing up structure. Obviously, we're not worried if it goes down structure because there's nothing down structure. So if it does continue to migrate up structure, as it will and should, we expect it to, we can, depending on the volumes, we'll start to see it in the first set of wells that are furthest down structure. And I would hope to believe that we also get a nice oil bank and we get some oil production. But honestly, CO2 floods in the LA basin have not been successful. There are no CO2 floods that have worked, and that I'm even aware of in the state of California, that have been economic. So, I'm looking at this as maybe kind of a shitty EOR, but I'm also putting CO2 away, which is a big part of it's really the main goal. That's the reason we're doing this. This wasn't a CO2 project that we went to find the cheapest CO2. We want to get rid of the CO2. Hopefully we can get some oil production in the process, but the reality is it's going to go up, and it should feed up structure as we see it in the first set of wells. Hopefully it'll be consistent with our model, or we'll have to modify our model to show that the fingering or whatever it is that we see that's different, because they'll be, where those wells are, those will be pressure sinks. So they should be the first to see it. And then we'll, again, if, there's a couple things that would happen at that point. If there's still a lot of fluid and it really is producing oil, then I may go to the additional effort of rerunning those wells with liners that are usable in a carbonic acid type situation, which is, I'd have to re-gut the whole of these old wells, or I got to abandon them. And in the likely scenario that I foresee is that we produce it until it gets to a point where it's too acidic, and we isolate that well and shut it down and then move up structure. Well, the wells will still be producing up structure, and we'll wait for it to get there. But we still should have plenty of wells between and us getting anywhere near any sort of faulting structure or any sort of pressure. We would, and the other thing that, and we'll talk about it again as a part of the permitting, the overwhelming issue that I have is being able to get people comfortable with this. So, obviously, if I just put in 1 meter of CO2, cubic meter of CO2, no one's gonna have a problem. And I put 2, no one's gonna have a problem. 5, no one's gonna have a problem. At what point does the pressure become, and if you remember the regulations, the way the LCFS is set up, they have this grid that says low risk and high risk. And if there's anything that's close to mid or high risk, I got to show how I mitigate it down to low risk. I don't know what that means, honestly, because it hasn't been tried yet, or at least as far as who I talk to. Everyone's like, okay, so how do I mitigate that? Well, I think the only way you mitigate it is you put less in. So what does that mean? So that's kind of what we're struggling with right now is, you tell me how much I can put in this area. I mean, I can do all the math, and I can show you, here's what should happen with the pressure. Here's what's connected. Here's where the front should go, blah, blah, blah. And I have, and when Richard talks, and we'll look at the future slides, they've done work, and they did it at Elisa Canyon. At what pressures do you have to worry about rock failure and closure failure? So if we run a project that's way below those restrictions, we're not going to get anywhere near Aliso Canyon sort of thing. Can I just get a permit that doesn't require me to do some crazy stuff? Drill monitoring wells, do this, 100-year bonds, that no projects will get done. I mean, that's what I'm struggling with is I start with looking at this project, and this is where I always scratch my head and I go, I've got the oldest, probably most depleted oil reservoir in the state, right next to the second largest landfill. And it's probably the cheapest cost of sourcing CO2, the shortest distance to connect it, and probably one of the best fields, at least in terms of just cavities of low pressure. and and it obviously captured oil and gas for 50 million years. If I can't get this project across the finish line, California is not going to get any projects across the finish line. I mean, that's the punchline. Because, as John has found, they found some nice closures offshore that had four-way closure. They're not faulted, but it's too expensive to get anything. Who's going to buy that offshore field and pipe everything out and deal with the Coastal Commission? And, that won't happen. So I'm thinking, okay, let's use this as a test project to get it across the finish line and start setting parameters so someone else can go out and do this and know, because the math's pretty easy. Once you tell me, now that I know what it's going to cost me to get the CO2 from the landfill and get it to my property, and I know how much it's going to cost me to drill the wells, the only other thing I have is, obviously how much I get in relief from 45Q and LCFS in terms of compensation to get rid of the CO2. It's a reverse oil well. I can do exactly the same math. I'm just, instead of producing and selling the oil, I'm injecting and selling the CO2. So, and I can do the math and I can back it out. And I can tell you the numbers are not great, even where we are, and how great this project can be, in terms of simplicity and closeness and the fact that it's doable because all the players now involved are on board. So it's all of those pieces. And I'm like, okay, let's do this. See if we can set a table of guidelines somehow that everyone can look to and say, you fulfill these, you're this conservative on your injection and you do this and you do this, you can fast track through CEQA and EIR. Otherwise, I'm going to spend the next 4 years in CEQA because I've done that, right? and there'll be people that don't want to do it. I can assure you that too, because that's always happens on every project I've touched. So, if I can get what we call a negative DAC, negative declaration, so I don't have to go through that process, and it shortens everything, and it's a simplified EIR, and I can get approval in a year, then I can maybe get this off the ground.
That would be amazing. All right, let's see. We have another question in from Mark Zobak.
Randy, I think Richard Schultz may address some of the pressure issues I'm concerned with in a minute, so I'll set those aside. But it would seem like a prerequisite for going forward is having a very dense seismic network installed so that you can keep track of exactly what's happening, where it's happening, and even if the big faults are no longer active in a geologic sense, there's probably a lot of little faults that are. And as soon as anything pops off, that's picked up on the local seismic networks operated in Southern California, you have to answer for that. And you should know more and you should know sooner than anybody else. And so it would seem like a very dense localized network, using some of the wells to put seismometers at depth is going to be a zero order starting place for you to get any kind of public acceptance of this project.
No, Mark, that one is a big issue, a big concern for me. There's no way, we don't have any historical seismic studies that have been done in the area. There's nothing. Again, we inject produced water and have been for however many years. Those volumes are significantly more than what we're talking about in terms of CO2 injection, in terms of volume, sheer volume. And we're not required to do that now.
If this were a homogeneous reservoir, and if you're taking out more than you're putting in, the pressure's going down and everything's fine. But it's the heterogeneities, the small faults that are cutting through that CO2 might access that weren't accessed before that could get you in trouble. And like I said, if something's happening, you want to know it before anybody else.
Sure.
So it's an easy way.
you know, Mark, maybe the question is, and I you know, I knew these are the big flags, of course. You know, one of the issues, or you know, is there, and from the work that you've done, because obviously, you know, it showed it conclusively in Oklahoma, and I watched that presentation. Is excellent. You know, right now, you know, we're running a couple thousand pounds below what was original reservoir pressure. So, you know, we're close there too. You know, we're about 1,000 pounds. And again, the original reservoir pressure was a couple thousand pounds more. You know, there's a long ways and a lot of injection that can be done that we stay well below the original, at least the reservoir. We're not pressuring it up anywhere near. And I honestly, given the amount of volume that's been pulled out of this, you almost got to empty Santa Monica Bay.
It's not Randy, it's not the reservoir I'm concerned with.
Right.
Everything that's surrounding the reservoir. Okay.
Right.
And those heterogeneities that might provide leakage pathways where there has not been a decrease in pressure due to prior production.
Right.
Okay. And that's, to me, that would be, you know, my biggest concern. Does
it, if you mix the water and CO2, again, in a carbonated water type format, does that make it simpler or easier? I mean, because I can tell you the punchline, Mark, is if I tell my board that, you know, there will be earthquakes, you know, there's no doubt, not because of this, I'm not saying because of this project, there are going to be earthquakes in the LA Basin. We're a very, very, you know, earthquake prone zone area. I mean, all of these faults across the LA Basin are obviously earthquake related for the most part, or plate tectonics related. So, you know, I guess it's going to be, if I'm going in with this idea that I'm going to have to try to prove that every time there's an earthquake in the area that I wasn't in some way responsible for it, then the project gets stopped. I mean, again, you start at some, you know, people, to be clear, and I don't mean to put it into monetary terms, but the economics on this aren't screaming good. They're barely get by. That's the point. And so, and if the goal really is to put CO2 in the ground in some place in some meaningful fashion in the state of California, you know, we're going to have to, I don't know what that means exactly, but I can tell you if I have to run a bunch of seismic machinery and keep that and prove everything, and then it's not worth it. You know, I don't mean to be negative, but that's the way it works.
Clearly an issue. Why don't we continue on and table that, but realize that we definitely have an issue.
Yeah. Hi, I'm John Harris. So yeah, a couple thoughts before we go on to the next page. First is, you know, these turbidite sandstone reservoirs, you know, many of the Pliocene and Miocene sands are being deposited as, you know, the faults are moving. And what you'll notice in both Ventura and LA Basin, if you go back through the development history of the fields, you'll see many dry holes that were drilled right up against the faults. And what happened is, you know, the workers back in the day who were trying to do the exploration and development drilling, you know, they thought that these sands would, you know, not pinch out, but, you know, truncate against the fault. And what we've seen in many places is because of the motion on the fault, you know, the sands tend to be pretty nimble, meaning you can have hundreds of feet of sand loss due to the topography at the time related to the tectonic activity and the faulting. You can see that these sands are very nimble. And so one thing, and you can kind of see this in the image on the left, is we're looking to identify individual sand bodies that pinch out before they get to the fault. So back to Sarah's original question is, you know, what happens if you have, you know, motion on the fault? Does that allow for gas leakage to the surface, the first step is to try to mitigate that from happening by identifying the sands that pinch out. And then the second thing that Dr. Zobak brought up, which is a really good point, the seismic monitoring now is relatively easy to facilitate and relatively cheap. They're passive seismic arrays or nodes that you can put in the field, wireless. It's not a huge burden in terms of capital. But having said that, the well density, these wells are drilled on less than 10-acre spacing. So, your well density maybe laterally isn't as high resolution as a seismic shoot, but, vertically, your seismic resolution that you would obtain out here is probably on the order of 20 or 30 feet, maybe 15. You have very high resolution data. It's not extremely modern, but it's a tool that we've been able to work with in the past. Most of the fields in LA basin are old, and I consider this industry standard for approaching sand and shale distribution by using SP logs. And luckily for us, these wells were drilled on less than 10-acre spacing.
Hey, John, a clarifying question. You mentioned that the sands are nimble. Can you tell us what you mean by that?
Okay, yeah, it's probably not a great explanation, but what you'll see is because you have topography being developed related to the tectonic activity and the motion on the fault, these sands are, deep marine turbidite sands. Any sort of topographic changes, the sands will feel and, not feel, but respond to in a relatively, nimble sort of way. And what I said was you can lose hundreds of feet of sand thickness over just 1,000 feet or so. So knowing that, combining that knowledge with, the data that Ben has shown, we should be able to identify sands that pinch out before they get to the fault, and we'll, inject into those sands. Obviously, there'll be an observation loop and through either well observations or passive seismic or a seismic array, as Dr. Zobak pointed out. Does that make sense?
Okay. Yeah, continue on.
Okay, so, on this, what we've done is, we've built a facies model. We've extracted geobodies from the facies. We've ranked them on size and therefore CO2 capacity. We've looked at connectivity, cross faulting that we think exists. And, we've identified, this one unit, this is probably more of an example than, this is exactly what we're going to do, but we've identified this Miocene C sand. And what we're doing now is just looking at kind of what the balance is between Randy's source from the landfill and what sort of capacity we would expect. That's important. Also, the rates at which we can inject are important, and all that will be fed back into Randy's economic model. And so that's where we are now. The next slide kind of outlines, what we're thinking at this point. And so, we know that the source of the landfill is producing 160,000 metric tons a year. So in order to inject that at surface conditions, we'd need to inject about 8 million cubic feet of CO2, a day. We're in the process of engineering, those wells, trying to understand, what sort of rates we can get at the given, reservoir pressure, different configurations for the well bores. As Randy pointed out earlier, those will probably be new drills because we want to make sure we, target the zones that are going to be, connected and isolated from, faults. So, over a 30-year time period, you're looking at about 91 billion cubic feet at the surface generated from that landfill. Given the current reservoir conditions, we believe that, compressing that CO2 at the depth of the reservoir would be at about 1.2 billion cubic feet. in the ground. So that's kind of what the source looks like and the expected rates. You know, probably be a handful of wells that would inject that 8.3 million cubic feet a day. And then on the storage side, so looking at what Ben's come up with, I think it was, you know, it was, 43 billion cubic feet of connected reservoir in that Miocene Sea. You know, we're looking at, you know, close to 1 million acre feet of gross rock volume. You know, we apply a net reservoir fraction. Not all of that zone can be filled with gas. We know we've got, you know, somewhere between a 17 and 21% porosity and a water saturation of about 35%. So, you know, our assumptions are that we'd be able to, you know, maximally put in, you know, 3.5 billion cubic feet of gas at reservoir conditions. So you can see that, you know, there should be room, we'll call it room or capacity for, you know, a multiple on, you know, the one landfill. So that's kind of the thought process behind rates, volumes, and capacity for the storage in that one zone. And one thing that's important to say is that you know, the Miocene Sea represents one of probably 4 units that could be used for storing CO2.
So can I interrupt? Yeah, so this is Sally. So just so I understand, sorry, I'm not used to these field units. So it sounds like that this Miocene sea sand has about 3.5 BCFs of storage, and the landfill gas at the 160,000 tons per year is 1.2, so that this sand could accommodate about 3 years of
That 1.2 billion cubic feet is a 30-year volume.
Oh, okay. All right.
Yeah, that's important.
Yeah, I mean, Sally, we looked at the 30 years because that's the likely life of the landfill.
Right. Yeah, that's fine. I'm sorry. I'm not used to these units. I think when you're talking to the people who've been working in storage a lot, sorry for this, they kind of stick with the metric tons and going back and forth between all these is just confusing. So, but
I got this like conversion chart because you're exactly right. I go tons and metric cubes to feet cubed, and we do everything in MCF per day. So it's been a nightmare trying to get because when I think of how much a well makes and how easy it is to inject, everything's in MCF per day and barrels. And so converting has been really complicated. We John and I went through this for a while yesterday.
Okay.
So yeah, sorry.
There's one thing too that Ben touched on earlier on the 3D model. You know, one other use that you know, we have for the model is, you know, once you have that corner point grid geometry, it's a relatively easy process of getting that into a reservoir simulator. So, you know, we have a high well control. You know, we have core data for, you know, identifying permeabilities, porosities, and saturations. And so, you know, a step that's going to have to be done before, you know, we actually start injecting is, you know, a reservoir simulation step. I kind of call the whole Petrel model kind of a you know, a common earth, you know, and engineering model. So, you know, with that, we'll be able to, you know, come up with an assessment of, you know, where the gas would migrate given the distribution of the sands within the reservoir.
Mm-hmm. Okay.
So these are just kind of cursory, high-level scoping analysis on, you know, does it make sense to go to the next step?
Okay, thank you.
Yeah.
Yeah, I just want to be mindful of time. It's now 2:17 and we just have until 2:30. So I just wanted to make sure everyone was aware of that and
Done.
everyone's thinking of any questions or other items for discussion and continue on.
Sounds like there's no more questions. Maybe we bring up Dr. Schultz for the following slides.
All right, thank you, Randy, and thanks for everyone being here. So we're back into containment space once again, and we've touched on a number of the issues. So I'll just step through these fairly quickly. We have 2 slides on containment, and the areas of containment that are kind of broad brush that we use to kind of bound our containment programs are site characterization, risk assessment, and monitoring plan. Really, the site characterization helps us to define the bounds for safe operation. That includes running reservoir models and other things like that. To do that, we have to generate first a full field model, then identify seals and their tightness. Okay, select a storage zone for which we can zoom in. Okay. As we're doing that, then we will be designing a pattern of injection and observation wells using existing wells wherever possible. And of course, designing a set of key performance indicators that'll help us to ensure that the gas is staying where we'd like to have it. Risk assessment really on identifying the main hazards of gas injection and proposing effective monitoring and mitigation measures. This step here brings up whether we use seismic monitoring of what kind and what locations. That all needs to be done and at sufficiently low cost, because this is a fairly small project, that we can actually get this off the ground while providing a reasonable assurance that we've done our due diligence and we've tried to capture the main hazards. These both flow into the monitoring plan, and it helps us to define both action plans for mitigation and also for compliance related reporting. So if we go to the next slide, please. There are 3 main strategies that we've been focusing on to kind of target our efforts. In the first one, we plan to take measurements to verify that there's no upward leakage of gas and therefore that we're maintaining seal integrity. This could be top seals, this could be stratigraphic pinch outs, it could be potential communication between layers. We have to check all those things once we decide on the target zone. And the best tool to do that is in-place measurements. So those will give us the constraints we need for reservoir models and for any additional theoretical work that someone might like to do. The second is to take measurements to monitor the plume growth, of course, and that'll help us to assess and hopefully verify that there's no undesired movement of gas out of zone laterally through the reservoir, or especially into boreholes that may provide leakage paths to surface if they're not characterized and treated carefully. The third one involves really measuring pressures near the faults that we can identify to really detect any anomalous pressure changes and then adjust our operations accordingly. So we're going to have to be a little bit careful with what's going on in the subsurface here. Fortunately, there's a fair bit of help. There have been other CCUS projects. There's been a lot of natural gas work. And they'll be, of course, used as a guide, and they have been guiding us through this point. These are things that we will focus on and hone in on once we take the full field model and really jump down to scale where we can measure these the pitch outs and the other characteristics in the detail that we need.
Yeah, and Mark, you know, when I look at this, the one that again gives me the most pause, because it's the hardest for me to get comfortable with how I need to mitigate it, and it's related to the seismic issue. And I would hope to believe there is a pressure that's pretty clearly falls below the pressure necessary to trigger, you know, faulting or earthquake, you know, energy related faulting. And I don't know if that's the case. I mean, obviously we don't worry about it as we inject water in in large volumes, and volumes that are significantly more than what I'm talking about doing here in terms of CO2 storage. So I'm hoping that I can, by being so conservative, fall below that issue. And to the extent that if I want to at a later date, push it higher up the spectrum of pressure to, to containment type parameters, then I have to prove it, more comfortably, or have additional mitigation measures or additional monitoring or something like that. Again, just to get these things kicked off, and started. I mean, it's, I feel like we spend, I'll be honest, I've spent so many years on this, I feel like I'm running in place sometimes. And so I hope that there's ways that we can get some of these started by setting low enough conservative parameters, but I'm not sure if that's even possible.
The reservoir models will help with that, and calibrating them with data, we'll check them as we operate.
Okay. Well, we wanted to show, we have the obstacles to completion. We also wanted to show you the 3D model itself. Looks like we've got a very few short minutes. I thought we had a couple hours. I would have talked a little faster. Again, I'm not in a hurry to go anywhere if people can stick around, but I have a feeling, if people can't, I'm not going anywhere.
Maybe we can cut to your last slide then, and anyone who stays put can view the 3D
model itself. Yeah, why don't we jump to the last slide, the obstacles to completion. Sorry, Ben, and John, because all the work they did on that 3D model, it's pretty awesome.
We'll see.
But anyway, you'll see the benefit. But as I say here, obstacles to completion, and I just can't overemphasize the permitting. Like everything in California, it's not easy to get anything done. So especially something as unique as this. I'm hoping that, with some pushing from whether it's Gavin Newsom or who needs to get behind the wheel to say, if we really want to get this across the finish line. And from what I understand, when you look at all of the studies that have been done, no matter how quickly we transition, if these CO2 concentrations are real and will, quote unquote, tipping point type issues, then this has to happen sooner rather than later. It's just not, you can't get there. So I feel like this is something that's obviously important. And to the extent that if I'm going into this with, obviously I've spent a lot of real dollars so far, but the next steps are really expensive. Now I'm talking about constructing and building pipelines and getting permits in that regard. And all the lawyers that I'm going to have to bring together at $1,000 an hour to get through the regulatory process. It's super expensive in multiple years, potentially. That's going to kill a lot of deals. So I don't know how we somehow, simplify that. And that's why I talk about this in terms of, is there a way of setting parameters low enough that everyone can get comfortable with the concept that this can be done without there being an issue, without there being, significant risk, and it's in the low risk category. And that goes across everything: proof of closure, seismic review and liability. This idea for the sequestration projects that you have a 100-year bonding liability, those don't even exist. So I don't know who came up with that, but from what I understand, you can't even get a 100-year bond. So short of putting all the cash up, setting it aside, which again makes it a no-go. And then the weirdness around the differences between EOR and sequestration, which really they're the same. So I find that one's also somewhat troubling, because it's at the same time, yeah, again, they're just different issues, but they're really relatively the same. The ones that I want to emphasize, so when you talk to government officials and you get in front of them, the one thing that really I pushed really hard on the carbon capture uses and storage roadmap team was this idea of access to the incentive programs. One of the things that my mantra has been that the true success of this project, of this potential, is really going to be driven by having, I think, more quickly, by having more people trying stuff, having more brains thinking about it, more people trying to crack the code, if you will, of how to do this inexpensively and get it in the ground. And why do we make it more complicated for small producers? You know, currently the programs are set up at 100,000 ton limits. You know, it was 500,000 tons before they came out with the changes a couple years ago with the influence from us. You know, and so, you know, I like as a good analogy is the you know, although different, the whole shale fracking technology didn't come from the majors. The majors take years to do things, and they're very conservative, and they don't do things very easily. You need someone to try stuff, throw stuff against the wall, see what works. And that's the sort of thing. And when I look, again, we wouldn't even have had this shale technology success without the Mitchells of the world that came in and said, well, what if you just blow the shit up a little more? You know, sort of thing, approach. You know, it's going to be the smaller guy that's going to figure this out. And for example, I have a facility that makes 25,000 tons, and I have an oil field that could take way more than that. But why not let me put my 25,000 tons away and compensate the guys for doing that? Those programs are going to get a lot more CO2 in the ground than waiting for the $100,000 plan. You know what I mean? The smaller guys are going to get this across the finish line a lot more. So that's just kind of a general concept. And then the last point I want to make before we get cut off in 1 minute, and it's a really one that's near and dear to me, and that's really all about the narrative here. And I really, this is an important point for me, because unfortunately the oil and gas industry is really being demonized right now in so many ways. And I really do believe that the oil and gas industry and the engineers and the teams out there are by far the best suited to solve this problem, and do it quickly and do it safely. And that's what I think is, and so if it would be, you know, I think it would be amazing if people could, you know, including Gavin, could come out and say, how amazing, let's let the oil and gas business help us solve this problem and turn this into a positive for everyone instead of such a negative for everyone. That's a soapbox issue.
I'm actually not going to cut it off, even though that we're at 2:30. I would like to personally see the model. And
okay.
So if folks want to stay on the line, that is fine. I've also seen a couple of questions come in through the chat, so I want to make sure that we address these. When is your thought on the timing of first injection? And a second one is there any incentive program you're able to take advantage of? Because it would seem like LCFS and 45Q are both not on the table for you. So those two questions.
No, I think 45Q, if I can get above 100,000 tons, it will qualify for me.
Okay.
So, and again, but it's above 100,000 tons. It's an industrial. I'll be taking CO2 from the landfill. I fall under the industrial permit. I did get clarification in the law, in the rules, that said that would qualify. LCFS as an EOR project, there's some ways to kind of noodle in, but I agree, it's not going to be easy. That is, you know, again, you know, it's funny. It's because it hasn't really been stepped through who qualifies and who doesn't qualify. Some people say you do, and some people say you don't. Honestly, I wish it was more clear.
Right, and the timing of first injection?
You know,
everything works out according to plan.
You know, again, for me, it's all about permitting. Again, what I haven't done, you know, I've talked to the Dogger. You know, can I do carbonated water? Yes, I could start doing that sooner, but it's not. You know, if I'm doing just carbonated water, I can't put 160,000 tons a year away. So I can't even do. It doesn't make sense for me to go over to the landfill and try to get their CO2. The carbonated water CO2 study would more likely be me taking the flue gas off of my generators. I have 10 megawatts of generation capacity, which is about 25 to 30,000 tons. I can carbonate my water with that. I don't need a permit, and I may do that. Again, but you tell me how long it's going to take me to permit, and I'll tell you how long it's going to take me to get to injection. That's always been the driver, Sarah. I mean, I know how long it takes me to build a pipeline. I can do it in 6 months or less. I can plan and drill a well in a couple months. I can build the facilities in less than a year by far, but that's not the driver here.
Okay, point made. And while we're waiting for this model to come up, one last question.
Yeah.
Aquifers and the groundwater quality, is there any monitoring of that nearby and any concerns with impacting that?
Yeah, we do. Obviously, the whole water board influence and CalGEM has been a big issue in the oil and gas business for the last really 5 years. As a result of the drought, which fortunately is no longer around, we've gone through a lot of different issues, or had to prove a number of things. So yes, I mean, we have to prove that our water injection program stays within the zone so that we have no water contamination anywhere, any possibility. And we have to prove it by showing cementing behind well bores and everything else. So it's a big battle, and we've completed what we had to do, and we've submitted it and are waiting for approval. We don't foresee any issues related to that. The big picture in terms of there being actually fresh water, it's quite clear that there is not fresh water in the Miocene and the Pliocene. The closest fresh water is above the Pico, and we have it's the USDW and the BFW cutoff. There's different cutoffs of where those fresh water characteristics are. The salinity parts per million are different depending on which category you use. But in any case, the point being, we have fresh water that's above the Pico, and we're fully isolated from it. And that's the punchline.
Okay.
It's part of the containment issue. I'm sorry. It's part of the containment issue because it's top to bottom, surface, near surface, and at depth. And we're working those as much as we can.
Okay, we have a raised hand from Sally.
I think Mark's hand was up before mine.
Oh, sorry, Mark. Mark, is your hand up new, or is it from before? Mark, you're on mute. Sally, let's go to you.
Sarah, I haven't been able to take my hand down. Sorry.
Okay.
There it is. Okay. There you go.
Yeah.
Okay, Sally.
Maybe I guess I'll sort of say kind of two things. So one of the things that we're working on a study together with EFI, which is the Energy Futures Initiative, which is a nonprofit, and I think they may do for-profit stuff too. I'm not exactly sure, but looking at CCS in California, making the point that it will be very difficult to achieve our emission reduction goals without CCS, and we are looking at a number of sort of use cases for CCS and trying to lay out a very clear picture of what are the obstacles for this. And it seems to me that, you've brought up a set of really important obstacles for the type of project that, as you say, could be an early mover. So I guess the first isn't really a question, it's a request is, how would you feel about us sort of sharing not this project, but just the challenges that you're facing as a small project without access to, really any incentive other than perhaps 45Q? Because I think these are really, really important. And anyway, so if you'd be willing to sort of let us share that, I think we could get, the word out that this class of projects, even though they're not the, million tons a year kind of projects, they are still very catalytic in terms of, paving the way for others to follow in your footsteps. So, so is that of any interest or not, or?
Sally, I mean, it's my goal. I mean, this doesn't get done unless I have full backing and pushes and support from all of you all. I mean, honestly, I mean, this is, you know, you saw the obstacles. Those aren't going away without some help. And I would love to get an audience with Gavin and talk through these and talk through, you know, I know he's working with the business school professor that has been talking through some of the you know, the cost issues and what it would take for CCUS to get off the ground in the state of California. You know, I basically told him the same thing I've just said here. It's permitting. You tell me, you show me a path of permitting, and I'll figure out how to get there. And that's how it kind of works. And so, you know, my likelihood of success and my ability to move forward with this project is greatly influenced by support from you all. You know, what I want to be, there's no pride of authorship here. I'm like, you know, I'm not, you know, this has been a passion project, if you will. That's, you know, I came out of retirement. It's my, you know, I'm really having fun and trying to figure this out. And really my goal and my, you know, and my pitch to KKR, if you will, and they write the big checks. And my pitch to them is, this is one of many. If this is really what's going to happen across the state of California, this is the first and most likely that I can see to get across the finish line. So let's do it. And so I convinced them to go buy this oil field. They didn't want to buy another oil field in LA. So, but they saw the possible ramifications of this, because if I can do this, then now we can roll it out. Because now I've set, you know, what I need to do is, like I said, if I had a template that said, you need to do X, Y, Z, this, you can only get up to this pressure given this sort of rock structure, you know, because what we don't have, like I said, is we don't have a bunch of salt domes here. We don't have any four-way closures. Everything in California, for the most part, is fault closure. So we're stuck with that. That's given. So, and the cost of moving CO2 from a source to an oil field is a huge expense in California, like incredibly complicated. And think of the protests, just putting any line in for anything. You know, so that is really more complicated than people believe. You know, there are pipelines all over, but you can't use them for CO2. You need to I mean, that you get carbonic acid real fast. It eats those lines in no time. So you can't just run CO2. So it's new lines that are stainless steel or carbon lined, or, you know, they're real issues. Similarly, trying to prove a negative, you know, and the seismic one that's the one that probably gives me the most pause. I can prove that there's no CO2 coming at the surface. I can see my wells, I can show the closure, but there are going to be earthquakes in LA and people start pointing fingers at each other. And I don't want them those fingers to end up pointed at me. Because then, you know, no one wins. And, you know, you can't prove that. So, you know, I did like to hear from John that as he said, because I'm not aware of how much it costs to put out seismic and monitor it. But I think the problem is even if monitoring it isn't a big deal, that's still not the problem then. The problem is when you do have some seismic activity in the basin, which will inevitably happen in my lifetime again, who's pointing at who?
Right.
So, and those are things, you know, he needs to get some clarity there. Again, we are moving forward. We're not going to slow down at this point, but, you know, it would be awesome for me, really awesome, to attach all of the people to this project and some PhD students if they want to have a real life project. You know, these are the things, the more the merrier for me. This is a project of passion, you know, passion project that I want to get across the finish line. who knows? So that's where I am. But honestly, if I, if all I hear is hurdles, and people don't want to be a part of this, then I may stop, because I am at that point where I'm going to be spending millions going forward. And if it's 5-year permitting process and I have no idea where Seismic's going to be, then it's likely I won't get the funding. I still have to ask for my money.
Right.
So,
Yeah.
Okay, let's take a look at this 3D model.
yeah, please.
Yeah, so this is that 3D block diagram we were looking at earlier. It's I'll see if I can turn on some faults. If there's anything else you'd like to maybe take a peek at, I can always turn it on and off and we can just play around with it.
Have you done any reservoir modeling of the plume that you can show in this model, or do you just have the geologic model?
We just have the geologic model at this point.
Yeah.
Have you developed 3D simulations of the plume and the plume migration?
No,
Okay.
we have not. No, this the purpose of this 3D model was to investigate the subsurface somewhat at a quick and inexpensive, relatively inexpensive manner, so that we can get to this point of being able to discuss whether these are going to be feasible projects. And we've gotten to the point where we've put in most of the data that we have, and with these connected volumes.
Yeah, and one of the
So
things
can
I
you
found out. Okay, I'm sorry. Go ahead.
Oh, can you, so that blue area is what you consider to be the connected volume, that's the Miocene sea sand?
Yeah, that was the one that I that piqued my interest the most when we were initially looking at these. I'll try and turn on some surfaces here.
And how thick is that?
It's, well, let's look at the zone. It kind of varies across the field. The zone would be just roughly, that's probably not accurate, a couple 100 feet, I would say.
Okay, so it's quite thick. Yeah.
Yeah, it's quite thick, and I mean it will pinch out, like in this it's called the east or the west Puente areas, where we're kind of zeroing in on. It's a little bit thinner, might get to about 100 feet thick at a certain area, and then obviously it'll pinch out to nothing at the edges.
And the reason we're looking over there in terms of injecting the most volume is it's the furthest from the urban encroachment. Where we have wells over on the far, what would be the eastern side of the field, the east side, we have wells that are intermingled between houses. That said, they've been producing for a long time, but they're the producing wells. And in fact, this may actually accelerate their abandonment, which is probably a positive thing for the community.
Right. And what do you think the permeability of that zone is?
I think I had the data on that. Bruce, is that about 39 millidarcy? We had like some average core data of about 20% porosity, and
yeah, we're dealing about 39, 40 millidarcies.
Okay, and then how many injection wells do you imagine? I mean, you probably don't need very many.
No.
I mean, if you were just doing this to get rid of the CO2, I'm kind of guessing one well would be fine.
Yeah, I mean, it goes back to that trade-off, and it goes to Mark Zobak comment about pressure close to the wellbore. As I inject, obviously the pressure, the higher volume and rate that I inject, the higher the pressure differential will be near the wellbore. So and permeate outward. So if I spread it out more, you get less of that pressure, less effect on any possible fracturing movement and so on and so forth, change in pressure. There is such a huge pressure sink here though, that, you know, again, 1,000+ pounds that I would hope to believe I can stay, you know, even, you know, I'm thinking, envisioning 2 to 3 million per well per day. That's, and I need 8 million a day on average to get to 160, and these are my metrics, sorry, MCF per day, but to get to that 160,000 tons per year, that's what I have to inject per well. And that's why I look at it, because I have wells that produce a couple million a day of gas. So that's how I know I can get it in the ground. But we've not, you know, we don't do gas injection. You know, that's not something we do. We do a lot of water injection. And again, I foresee that, you know, if I'm focusing 100% on just EOR, then I'll work with Tony, and Tony's work has shown quite clearly that carbonating the water, training the CO2 in the water will give me a better sweep efficiency on this sort of vertical bedding. Otherwise, the CO2 tends to finger and go in different directions. And albeit, I think if I put it low enough, the thing also about the CO2 is it really is attracted to the water, and the water will absorb quite a bit of the CO2 in solution. And above 1,000 pounds, you've taken, you know, something that was 500+ cubic meters at the surface down to 5 meters. It drops by a factor of 10 when you compress it to 1,000 pounds. So now it's almost a fluid, and you mix it now with water, and it'll you know, that I really think we're not gonna have free gas from it. Is not what I visualize, but again, we need to model it, but that's not what I visualize.
Right. So what is the water saturation in that layer right now?
Oh my gosh. I'm not even sure what the rough number, you know, I think it's 80% total water, including in situ, you know, water. So, I mean, we're running our gross, our average depletion is only 18%. So we've only gotten 18% of the original oil in place.
Okay, so it's basically most of the fluid is oil. There's a little bit of water, but the pressure is low because it's a closed unit.
Correct.
I see. Mm-hmm. Yeah. Yeah. So do you have any geological detail within that zone itself? Have you looked at you know, well logs and
all of these wells, all of the well logs are in the system. All of these pics are driven directly off those well logs. Mm-hmm. So everything has really been driven from that data. And so all of the different you know, layers, if you will.
Maybe Ben, you can turn on the SP, you know, the wells.
Yeah.
Logs.
Trying to do it in a way that doesn't turn on all the logs at once and lock this thing up.
Oh, okay. Yeah.
So I'm just turning on the Puente wells here, which is those lease wells, and then we can turn on. I'll turn these off.
Oh, and is this miscible injection or immiscible? Like
no, it'll be immiscible. We're too low pressure, I'm pretty sure.
Mm-hmm. Right. And what's the viscosity of the oil?
It's what is it? It's depending on where you are, it looks like it's between 18 and 31 gravity.
Okay.
So there'd be more zones there's some zones that, you know, given the right pressure, you'd be able to obtain miscibility.
If we pressure up enough.
Right.
You know, again, Sally and Sarah and the whole crew, Tony and Mark, it's, you know, we're kind of taking baby steps here. And, you know, again, it's, you know, we're given that we've got this really large container and the source next door, it isn't the biggest one, but it's, 160,000 tons. And if I can take it off, end up ultimately take it off the flue gas, 270,000 tons, that's still a meaningful amount of CO2. And if I can, again, start this program and get it going, such that we can start kind of heading off potential issues as we learn more. I mean, again, I think that this is, I'm sure we'll figure more out as we, obviously as we go through this, and we'll pick, I feel comfortable that we can handle the next 30 years of, I can tie in the landfill and I can handle 30 years of that CO2 coming out that landfill. And then if it works, and I can get everyone on board and everyone's getting comfortable with it, then I can go to Whittier and get their gas and bring it over. But the beauty from my perspective, I'm thinking, okay, here's the second largest landfill in the middle of the LA basin. And I'm right next door, and it's been there before the LA even got here. So it was 135 years ago. Why can't that be right next door and be a waste gas storage facility? Again, this concept of repurposing this, we use it as an oil field. Now let's put everything back in there and then close it down, just like the landfill, and move on. And we can do that across the basin. I mean, there are so many large fields, but this one in particular has some of the best qualifications than any other field does.
I think what's been so enlightening about this discussion. I do want to kind of bring it to a close given the time here, but you've got so many great attributes of your source and sink. You couldn't be better lined up. And then it's just a matter of figuring out how would you get this through the California process, and can one get a project like this through the process? And there are a few things that are a little bit warts on this. You are rather close to a populated area. And there's the seismicity issue. And so it's not wart-free, but on the other hand, it's got elements that are lining up. So thank you so much for presenting. Let's definitely keep in touch, both as Sally mentioned, because we're doing further work in California that we hope to use to influence some of the process and what's going on in the state. And this is obviously a very good example of a project that's got a lot of the right elements that could use some assistance. So let's keep in touch.
So can I just ask one question? So, I mean, if there is somebody who would be interested in following up and working on this, what would be the next step? What should we do?
Call me.
Okay.
Seriously, I mean, call me. I think about this I think about this project all the time, and I love to talk about it. And so,
you're gonna hear from us.
I really want to use this. I would really like to be able to use this as a template of figuring out how to solve these issues and get this across the state in a fast track fashion to really make this work. And so whatever you all think would help in that would be amazing. I've been fortunate that I've been able to touch a lot of the right people because of not only my affiliation with Stanford, but of KKR, because they know a lot of really important people. So I have friends like Dave Rogers and Jeff Brown, who wrote a lot of the regulations and are Stanford law professors. And these are all friends of mine. We're fraternity brothers. So I'd love to be able to figure this out. That would be the beauty for me, and I'm willing to spend a lot of effort to get it across the finish line. So,
well, we would like to see a CCS project go forward in California.
Yes.
That's like we have some common interests here. So
it'd be great.
We will talk at the Sally, Tony, Mark, myself, others, Lynn, and we will be in touch.
All right. Thank you so much.
For having us.
Yeah,
Great to see you, Randy. It's fun to hear about the project. Lots of good stuff.
Thank you, Lynn. Really good to hear from you as well.
Take care, everyone.
All right. Thanks,
everyone.
Thank you.